Hi, my name is Nick Mignano, and my topic for this presentation is a two-species diffusive jet. That is, a jet of species A into species B with diffusion. This is a fundamental problem in combustion because it is one of the simplest geometries to sustain a non-premixed or diffusion flame. For example, it could be a jet of fuel burning in open air, or a fuel jet burning in coaxial oxidizer flow within an enclosed environment. And so I have performed a 2D simulation of a jet of one species within co-flow of another, as shown in the diagram below. Now, I'll discuss some of the theory for this problem and what I will be comparing my numerical results to. There are many assumptions that go into the analytical treatment of this problem as listed on the right, but I will specifically note what is called the flame sheet approximation. This just says that we have infinite rate chemistry, and as a result, the fuel and oxidizer react in a very thin region that we consider to be the flame. In other words, the flame is infinitesimally thin and lies exactly where the reactants are in stoichiometric proportion, as shown in the diagram in the middle there. Now, the earliest and most well-known treatment of this problem was performed by Burke and Schumann, but their solution was fairly complicated. We can make it a lot simpler by just assuming that the density is constant, that we have isodensity flow. With that assumption, the flame length, that is the distance from the outlet to the flame tip, is given in the equation shown there, with where D is the mass diffusivity, Q is the mass flow rate, and Y is the stoichiometric fuel mass fraction. The constant density assumption is not actually very accurate for a real combustion system, obviously, but it does make the stoichiometric mass fraction isocontour indistinguishable from a non-reacting case of the same species. This means that we can find the flame shape and the length without actually having to model the reactions if we just simulate the mass fraction field, as I will go into now. So this brings us to the simulation methods. The artificial compressibility method is used to solve the Navier-Stokes equations, solve for the entire velocity and pressure field of the jet. In addition to that, we also solve for the mass fraction z by discretizing the z equation, which, to get to that equation, we also assume that we have constant diffusivity and that the species have the same diffusivity. The Euler explicit solver is used for the Navier-Stokes equation and solving the z equation, and the convergence of each case is determined by the L2 norm error. The inlet boundary is set such that the mass fraction, the z, within the fuel stream is 1, and outside of that, it's 0 everywhere else. Or on the inlet, anyway. Now to some examples of the results. So shown here are some examples of the mixture fraction field as the inlet velocity is increased. The red line represents the flame position, that is the stoichiometric mass fraction isocontour for a example reaction of hydrogen and oxygen. So if there was a different reaction, that stoichiometric line would lie elsewhere, but for hydrogen and oxygen, it would be at that position, and that's what I'm basing the flame length on. We can see that the flame length increases with the velocity, which makes sense intuitively and is also consistent with theory. Here we can see that the flame length shows a trend that is close to what is expected from that constant density expression, but there is some discrepancy, especially at higher U, likely just due to some error in computation that I couldn't fix, or maybe it wasn't quite reaching convergence. But still, overall, pretty similar to what is expected. So in conclusion, a numerical method for computation of the mixture fraction field for a jet and co-flow was created. With several assumptions, this can be used to observe characteristics of a diffusion flame, and the general trends in flame length were consistent with the results of the simulation. Thanks for listening. Any questions? Here are references.